poison it releases. So something over here is like cat is dead, and no, cat is alive. Okay? The poison is not released. Okay, cat is dead and the poison is released. Okay, so in the cavity, it's possible to maintain this coherence, but that's basically considering only when the cavity is completely closed off. When we actually put in the coherence, we see that we will have it's not possible to maintain this kind of coherence. So what we will get is, if I write down the density operator at this level, if I write down the density operator here, I get G minus alpha. Maybe I should use the correct product. Minus alpha minus alpha. Okay, that's one term. And then alpha. Okay, so these would be the macroscopic states, right? And if I was writing a statistical summation, I would just write down these two terms, where you have a cat being alive and the poison being not released. Okay? And there's a classical probability associated over here. Cat dead and the poison released. Okay. But
the product you have between G and
yeah, there would be a direct product again. So over here, but then with this state, the density matrix contains off-diagonal elements. And those off-diagonal elements, I'm not going to write them down. This is like G and direct product space with minus alpha. So what's bothering people is this term, and also over here, right? So the cat being dead and alive at the same time. So we will show that this thing is not going to be. This thing is going to decay away very fast, and it's much faster than the time at which the energy is going to be lost from this cavity. So that's probably what we will talk about on Thursday. So I guess we can end here today. If you have any questions?
Just one thing about the Ramsey interferometry.
Yeah.
So it's like if you want to do single qubit gate.
Single qubit gate. Okay.
Do you need to use the Ramsey interferometry, or we can just shine light on the qubits and then take down the Planck sphere?
We can. I mean, ultimately,
Just
maybe I can talk a little bit about realizing these.
Because I'm just curious. For example, if you are using on track, you cannot really like the whole thing. It goes through all these things.
Right. What you want is effective Hamiltonian. As long as you have some effective Hamiltonian that looks like one of these things, okay, then you can do this, because you have two-level system, okay, and two-level system can be mapped onto the block sphere. Your two-level system can be mapped onto this block sphere, and we know that what happens for the spin, right? If I subject it to some kind of field, okay, I can make this rotate however I want by controlling the three components of the field. So to really have what's called a universal quantum gate, you want to be able to have three single base gates, right? You want to be able to add a phase shift between the upper and lower state. You want to be able to rotate them like in the Ramsey thing. And then you also want something else. I don't remember, maybe a control mount gate or something. Yeah. Right. So anyways, all those can be, so long as your system can be mapped to this two-level system thing. Remember, we always work with this sigmas and so on. So long as you can construct those effective Hamiltonians, like whether you have cavity or you have superconducting circuits, Josephson junctions and stuff, or maybe an ion trap. I know that in Jerry and Knight, in chapter 10, they talk about ion trap. Maybe we can take a look at that. And they tell you how you can realize. They tell you how you can realize this James Cummings model as well as this dispersive Hamiltonian in the ion trap system.
So basically, you are trying to find the complete Hamiltonian simulation of James Cummings.
Yeah. But actually, before realizing the James Cummings model, the James Cummings model is something that can give you a set of universal quantum gates. Before that, there are two other. I think there should be some other. So there are. You can look this up. Something called the Chandler criteria. Right? So to actually do quantum computing, the first thing you need is a stable two-level system. So basically, you want an atom and a way to isolate the interaction so that it only happens between these two states. Okay, so that's the first thing you do. Or you do a spin system, which is of course stable because there's only two such states. Okay. So the first is stable two-level system. Okay. I think the second is a way to prepare the input. To prepare the states into a certain input state. Okay. The third one is what we want with the third one is the third one is to be able to produce a universal set of single qubit quantum gates. And the fourth one is like you can read out the effects of measurement. I don't remember the order, but that's roughly the first four.
So the universal gate has two qubit gate and one qubit gate.
Yeah.
Separate.
Yeah. You guys can look this up. Okay. I don't remember the order in which they go.
Did you keep the references for your lectures today, or what books or what papers?
Oh, this is still just today we're taking material from Jury and Knight. And also the book by House, Herman House.
Herman House.
Yes. But so Jerry and Knight is called quantum optics or introduction to quantum optics. Herman House's book is something to do with quantum noise and optical measurements. I forgot the name of the book. Okay. Anyways. And then that Ramsey thing, that's talked about in many experiments. I think it's even on Wikipedia. Yeah, you guys can take a look. So yeah, I guess I'll see you on Thursday.
Okay.